Okay, so we next look at alternating series test. There is that type of series where the terms alternate between positive and negative terms. So this proposition is about convergence of such series. Here we have a sequence an of real numbers which has two properties. One is that all the terms in this sequence are non-negative. All the ans are non-negative real numbers, and the terms are decreasing in this sense. An is greater than or equal to an plus 1, the n plus 1th term for all n greater than or equal to m, because that's where the index is starting. Then look at this series. To make it have the alternating nature, we have multiplied an by minus 1 to the power n. Because the ans themselves are non-negative, so we will have positive and negative terms. Of course, some of them may be 0, but just I am saying that there is an alternating nature in the terms of this series. Then this series is convergent if and only if the original sequence an converges to 0 as n approaches infinity. So this is what we want to prove now, and this proof actually is there in the text. It's not left as an exercise. As is common with this kind of things where you have to prove two implications, one of them is easier than the other. So we tackle the easy one first. First, assume that the series is convergent. Because the series is convergent, we can apply the zero test. So by the zero test, this limit is 0. And hence this limit is also 0. The reason for having this from this one is this. Since the distance between this thing minus 1 to the power n times an and 0 is the same as the distance between an and 0. So you can clearly see that if you apply the definition of limits to this limit, then there you have this distance or absolute value less than or equal to epsilon for some other conditions which you already know. So this will be less than or equal to epsilon. In other words, because of this limit you can make this distance as small as you want, so correspondingly this distance also can be made as small as you want, and hence again by the definition of limits this limit is also 0. So that is one half of the alternating series test. Now we go to the comparatively more difficult half. So in this half we have proved that the condition that the sequence an converges to 0 is necessary for the convergence of the series. We will now prove that it is sufficient also. So conversely, let this limit be equal to 0 for any integer n greater than or equal to m, let Sn denote the partial sum of our series, specifically this. Sn is defined to be this partial sum. M to capital N. Our aim or our job is to prove that this sequence of partial sums converges, because then by the definition of series convergence, this will also converge to something, some real number. Okay. Now observe, okay, so now we have to slowly move towards this conclusion. First of all, we look at this calculations. Sn plus 2, where n is of course our this n, any n greater than or equal to n. Now Sn plus 2, because of what Sn is, which is a finite series, this can be written as, do I have space to write it here like this? It's better to continue on this side. Sn plus 2 is equal to Sn plus the next term in that finite sum, which is minus 1 to the power n plus 1 times an plus 1 plus the next term minus 1 to the power n plus 2 an plus 2. Now we can take minus 1 to the power n plus 1 common out of these last two terms and have this equal to Sn plus times an plus 1 minus an plus 2, because we have one extra minus 1 here. Now, since our original sequence an is a decreasing sequence, so an plus 1 will be greater than or equal to an plus 2, or in other words, this difference will be greater than or equal to 0. So that means the sign of this term is entirely determined by minus 1 to the power n plus 1, or more specifically by n itself, that is whether n is even or odd, because this thing is non-negative. Hence, so what is going to happen when n is, say, even? When n is even, n plus 1 is odd, so that means we will have a minus sign here. So we are subtracting a non-negative real number from Sn to get Sn plus 2 when n is even. Hence, Sn plus 2 is less than or equal to Sn if n is even and Sn plus 2 is greater than or equal to Sn if n is odd. When n is odd, the exact opposite thing will happen, because then n plus 1 is even, so we will have a plus. We are adding a non-negative real number to Sn to get Sn plus 1. So Sn plus 1 will either be the same as Sn precisely when this is 0, otherwise it will be strictly greater than Sn. Okay. Now next we are going to draw further conclusions from this situation in the next paragraph. To do that, we are next going to take not just any integer n, but any even integer n. Now suppose why exactly we are going through these calculations, that will become apparent quite soon. Now suppose n is even, then from the above discussion, that means this thing, and induction, we first of all have this. This means in its place we have a more general statement. Sn plus 2k is less than or equal to Sn for all natural numbers k. Now where is this coming from? This, of course, you can probably guess, is coming from this inequality. Let us see how. And what exactly does the author mean when he is saying that by the above discussion and induction? You see, what he means, of course, is that this inequality follows from induction and from this inequality. When k is 0, when k takes the smallest possible value, then of course you have equality, because on both sides you have Sn. And when k is 1, this inequality reduces to this one, which is true, we have seen here itself. Now next, the higher values of k also give us the other inequalities in this way. How does one guess at these inequalities in the first place? Say you take k equal to 2, then you get Sn plus 4. Now because we have chosen n to be even, so n plus 4 is also even, and in fact n plus 2 is also even, because n has been chosen to be even. So in this inequality, if you replace n with n plus 2, you then get this thing, which you can do, because now you see this inequality is true when n is even. Now n plus 2 is also even, so we are having this, and this again of course is less than or equal to Sn. So Sn plus 4 is less than or equal to Sn. Just like that, Sn plus 8 will also be less than or equal to Sn. In general, one can guess that these inequalities are going to be true, and that is true, and in proving that one can use induction. So that's what the author is saying here. So that is one thing. There is another thing also. We have Sn plus 2k plus 1 greater than or equal to Sn plus 1, which is equal to Sn minus a n plus 1. For all k, actually we should mention that for all natural numbers. Okay, now where are these next set of inequalities coming from? They are coming from this. How? See, for these inequalities we need n to be odd. Our n is not odd, it is even, but then n plus 1 is odd. So if you think of n plus 1 here in place of n, what do you get? Say you replace n with n plus 1. You then get n plus 1 plus 2, so that means n plus 3 is greater than or equal to Sn. Then here also again, if you replace n with n plus 1, or here itself if you replace n with not n plus 1 but n plus 3, say, because n is even, n plus 3 is odd, so this inequality works when you replace n with n plus 3. So this side will become Sn plus 5 and that side will become Sn plus 3. So this is greater than or equal to Sn plus 3. So you can see that all the odd integers are appearing here, 3, 5, then 7, 9 and so on, which are all of this form 2k plus 1. So these inequalities can also be proved by induction on k, where k is a natural number. And what about this thing, Sn plus 1 becoming Sn minus an plus 1? That is coming from the definition of the partial sums Sn. You see, Sn plus 1 actually is what? Sn plus minus 1 to the power n plus 1 an plus 1, because our n is even, n plus 1 is odd, so that is why we have a minus sign here, Sn minus an plus 1. Okay, so we have got two sets of inequalities. Each set has infinitely many inequalities in it. Moving on. So from here then where can we go? Finally, we have these next calculations. Sn plus 2k plus 1. We have already written something involving Sn plus 2k plus 1, but now we are going to write something else. Sn plus 2k plus 1 is what? Sn plus 2k plus by applying the meaning of Sn plus 2k plus 1. We go till n plus 2k and then one extra term. Again, because n is even, so n plus 2k plus 1 is going to be odd. So that is why this is equal to Sn plus 2k minus An plus 2k plus 1. Now, because all the terms in our original sequence are non-negative real numbers, so we are subtracting a non-negative real number from this to get this. So this will be less than or equal to Sn plus 2k, equal to if this is 0, otherwise it is strictly less than Sn plus 2k for all natural numbers k. So now we combine all these things. Thus we have this. First of all, we write this Sn minus An plus 1. An plus 1, we found that to be less than or equal to this thing. N plus 2k plus 1. This is less than or equal to this. Now here we have found that this in turn is less than or equal to this Sn plus 2k, and this in fact has been turned out, we have found that to be less than or equal to this Sn for all k belonging to the set of natural numbers. So now we can write something in place of these inequalities. In particular, now in place of these inequalities, if we write something like this, Sn minus A n plus 1, which of course is just this, that is less than or equal to Sn, which is less than or equal to Sn for all n greater than or equal to m. Will you understand? That is, do you realize how we have concluded this from this? Where have these Sn plus 2k plus 1 and Sn plus 2k vanished, and in their place how are we writing Sn? You see, you can write two sets of inequalities in place of this chain of inequalities. One of them looks like this. Is less than or equal to Sn for all natural numbers k, and at the same time we also have these. Now, what do you think we cover as we vary k? I mean, what are the terms in the original sequence? Actually, although we wrote the sequence of partial sums with this suffix n, but because we have chosen that n to be some particular in here, let us denote the sequence of partial sums more simply like this. Now, as you vary, both these sets of inequalities are true, and in fact they are true for all natural numbers n. Now, as you vary, for example, in this second set of inequalities, as you vary k over n, what are the terms that we get? We get Sn, which lies here in the middle. Then we get Sn plus 2, Sn plus 4, etc. Okay, and it goes on and on. As k increases, so does Sn plus 2k correspondingly. Whereas in this first set of inequalities, if we similarly vary k, then the terms we cover are Sn plus 1, Sn plus 3, Sn plus 5, and so on. So you see that combining these two sets of inequalities, that is here, we actually cover all the terms in this sequence Sn, but actually not in fact all the terms, but all the terms that start from n. So that means we are saying that this thing is less than or equal to Sn, which in fact is less than or equal to S capital N for all okay. I said something and I wrote something else. For all n greater than or equal to n, because these are the terms that we have covered in these inequalities. So in place of this, we can also write more compactly. We are writing the same thing, but more compactly we are writing this. We do lose a little information in making this conclusion though, because we don't write anything about this relationship between the even suffixed and odd suffixed terms, but that is not something that we need now. We need only this. Okay, so we have understood these final inequalities. Now we are almost there. Now note that we can in fact write something else also here, which will be necessary for what I am going to do next. Instead of simply writing these inequalities, we are going to write a little more. Sn minus an plus 1 of course is less than or equal to Sn, which is less than or equal to Sn, but that itself is less than or equal to Sn plus an plus 1 for all n greater than or equal to n. And where is this last inequality coming from? It is true because of the fact that an plus 1, this last term, is a non-negative real number. That is, now look at this extreme term, this middle Sn, and this extreme term. So that inequality involving this one Sn and this one, those inequalities are equivalent to this. Okay, so we let these inequalities stand, and now we concentrate on the fact, having gone through these calculations. Keep in mind that so far we have not actually used the hypothesis that we have in this part, that the sequence an is converging to 0. Now we concentrate on that. Now we are going to use that. So we choose our positive real number epsilon. Since limit of an is 0, there exists an integer m greater than or equal to m such that an minus 0 is less than or equal to epsilon divided by 2. For all n greater than or equal to m. Okay, so this is just we have used the definition of limit and the fact that this limit is 0. That is, because our an's are all non-negative real numbers, we get this. 2an is less than or equal to epsilon for all n greater than or equal to m. Now looking at these inequalities and these inequalities, you can clearly see that we can combine them because of this intermediate an terms, and that's what we are next going to do. Keep in mind that this entire calculation that we went through after choosing that even n depends on that n, and there was no restriction in our choice of n. The only restriction was that n should be an even integer greater than or equal to m, and there are of course infinitely many even integers greater than or equal to m, and it's an unbounded sequence of integers. So no matter what this integer m is, we can choose one n conveniently which is even and for which n plus 1 is greater than or equal to n. And for that particular n also, all those things will be true, and so ultimately these inequalities will be true for that choice of n also. Now suppose we choose an even integer n sufficiently large such that n plus 1 is greater than or equal to m. Okay, then for all integers n and m greater than or equal to this specifically chosen n, we have, okay, now again we are going to go through a sequence of steps. First of all, we write Sn minus Sn. It's the absolute difference. Due to the triangle inequality, in its place we can write Sn minus Sn plus Sn minus Sm, and we will have this inequality. Okay. Now we can replace these terms in this sum by the corresponding terms here, but is that justified? That's the thing. That is justified because you see we have chosen, or let me just first write the thing down and then I will say what we have done here and why that is okay. That means we have just simply used these inequalities here in both the cases. That is, you can do that provided this suffix n is greater than or equal to n. It is, and the same is true for m also. M is also greater than or equal to n, and because we are dealing with absolute values, so the order does not matter. In fact, this is the same as the absolute value of Sm minus S capital N. So that means we can write like this, which becomes then this last part of the proof is not this elaborate in the text. However, I decided to show these things. The author simply mentions that it can be done. So this becomes equal to 2 times an plus 1. Now 2 times an plus 1 is less than or equal to epsilon. Why? Because here see, what do you need for this to be true? That this suffix n be greater than or equal to n. Here our suffix is n plus 1, and that's how we have chosen things. So this also is less than or equal to epsilon. So what we have managed to show is that for any positive real number epsilon, there exists an integer n greater than or equal to small m. In fact, let's just conclude our things so far. So we have shown that for every epsilon greater than 0, there exists an integer n greater than or equal to m such that this for all n and m greater than or equal to n. You still may have one small confusion, and that confusion is likely this thing: how is this chosen n greater than or equal to, oh, wait, we already have m in our original sequence, so we cannot use m here. So what shall we use? So let us use p and q then have to modify the things accordingly, because we are not doing algebra but analysis. We don't have that confusion of thinking of p and q as prime numbers. So now we have this such that for all p and q to be greater than or equal to n. So that confusion I was talking about. How are we concluding that this n is greater than or equal to n? Because you see, n plus 1 is greater than or equal to m. Okay, so what will that imply? That n is greater than or equal to m minus 1. Now I will have this provided m minus 1 is greater than or equal to m, which is not how I chose things, right? So you just choose, I mean, wherever we encounter this m for the first time, which in fact is coming from this limit now. There, instead of choosing capital M to be greater than or equal to m, you choose it to be strictly greater than m, because you can choose any integer in fact. If you encounter an m, you can choose an even higher m, that will also automatically work. So with this choice, so you just write this modification there, where we wrote capital M for the first time, instead of writing greater than, you have greater than or equal to. Then your capital N is guaranteed to be greater than or equal to small m. So that's how you get this thing. And why are we insisting on this so much? That is because our suffix values are starting from m. So if your n falls below that, then a suffix n does not have any meaning. Anyway, so we finally have this. Hence, this now is a Cauchy sequence. And hence is convergent. We already have proved that Cauchy sequences of real numbers are convergent. So that is the second half, and this completes the proof. And hence is convergent, and that's it. So that is our alternating series test. Now let's see one example which illustrates this test. This is example 13, item number 13 actually. The sequence of reciprocals of the positive integers is non-negative. Sequence is non-negative means the terms are non-negative real numbers. Is non-negative decreasing. As n increases, the reciprocals decrease and converges to 0 as n approaches infinity. That means this sequence satisfies all the conditions given in the statement of the alternating series test. So by the alternating series test, this series is convergent. And if you already have encountered this series, you will know that this series, if I am remembering correctly, converges to the natural logarithm of 2, something like that. However, if you take the absolute values of the terms of this series and consider the corresponding absolute series, okay, which we consider when in the definition of absolute convergence. Then you get this series, which has the name harmonic series. This series is divergent. We will see this in the next section, why this series is divergent. In fact, in the next section, we will prove that not just this harmonic series, but an entire class of series which look like the harmonic series. Some of them are convergent and some of them are divergent. We will prove a result to that effect. Is divergent, and for this corollary in the next section, 737. So this is an example of a series which is conditionally convergent. That means simply just convergent, but not absolutely convergent, because this series obtained by taking the absolute values of all the terms diverges. So we see that a conditionally convergent series like this one need not be absolutely convergent. Although every absolutely convergent series is conditionally convergent. Which is a result recall that we already saw in the previous video. We did not prove it, we will prove it in the exercises. Now, just like we have properties of finite sums, properties of sums over finite sets, we next have similar properties of series laws. So that is the next result. Proposition 7 to 14 series laws. Although we will prove this law in the exercises, but the hard work has already been done in proving the finite series laws and the limit laws in the chapter on sequences. Using them, these laws are just simple consequences. So just like those things, this also has parts. If summation an is a series of real numbers converging to a real number x, and there is another thing, instead of writing so much, we at once write like this: if this and these are series of real numbers converging to x and y, respectively, then the series whose nth term is an plus bn converges to x plus y. You can clearly imagine how one can prove this, in fact almost immediately, using the sequence laws and using just the sequence laws, that's it. That is, because we also use the symbol for a series to denote its sum, we can write all these things at once like this. Plus summation Pn. So that is part A. Then part B. Part B, I think, involves a series and a real number. Yes. If this is a series of real numbers converging to x. Whenever we say converging to x, you should understand that x is a real number. And if C is a real number, then the series CAN converges to Cx, that is so it's like taking C common out of all the terms, the series version of that infinite series version. Next, part C. Part C is it involves one series and that other series obtained by removing some terms. Let summation n varying from m to infinity be a series of real numbers, and let k should be a non-negative integer, because if k is not non-negative, things will not make sense. K be a non-negative integer. Then the series, the original series, converges if and only if this other series where the index starts from m plus k converges. If this converges, then this converges, and if this converges, then this converges. And when any one of them and hence both of them are convergent, we have this identity involving their sums. And this identity is quite natural and looks like something that should be true, and it is true. M plus k minus 1 plus so when both of them are convergent, then this series equals this finite series where the index varies from m to m plus k minus 1 plus this infinite series where the index then varies next from m plus k, and it goes on and on. And finally we have part D. Let summation an n varies from m to infinity, be a series of real numbers and k be any integer. So k is not necessarily non-negative, k can be negative also. Then this series is convergent if and only if that other series converges. Oh, okay. Series of real numbers and k be an integer. Oh, so it has been, in the beginning itself it has been considered to be a convergent series. Anyway, we can write that like this also. If our original series converges to the real number x, summation a n minus k, where n now is varying from m plus k to infinity. So we have written m plus k in place of m, and to compensate for that we have written n minus k in place of the suffix n. Also, converges to x, and that's it. This is the statement of the series laws, and its proof is one of the exercises which we will solve when the time comes. See exercise 7 to 5. Now there is a little discussion from this proposition, that is the series laws, part C. Seven to 14c, we see that is this one. Even if you remove finitely many terms from a series, from the beginning of a series, the whatever is left, that will form a convergent series provided the original series was convergent. And the converse is also true. If this tail end of the series is convergent, of the original series, this is the tail end. No, you can decide to cut the series into two halves. But the first half, of course, will be a finite series, and the remaining tail will be an infinite series. So if the tail is convergent, then the original series is also convergent. So that means the convergence or lack thereof of an infinite series is unaffected by the removal of a few terms from the beginning, or unaffected by introduction of new terms in the beginning. The value of the sum, of course, will be affected. For example, this series sum will be equal to this series sum plus something extra. But the convergence or non-convergence, that is not affected. So that's what the author says. We see that convergence of a series does not depend on the first few elements of the series. The situation is just like sequences. Whether a sequence converges or not, that is unchanged if you remove a few terms, finitely many terms from the sequence. The first few elements, though of course elements of the series, it affects those elements to influence which value the series converges to. That is something that follows from part C. Because of this, we will not usually pay much attention as to what the initial index M of the series is. Yes. Now it may sound a little bit strange that we are not going to pay attention too much to the initial index, and thereby if we remove some terms from the series, from a convergent series, the convergence will not be affected but the sum will change. So are we not concerned about the sums? Actually we are not concerned about the sums or the exact values of the sums. We are more concerned about whether a given series is or is not convergent. We are going to investigate that thing. To see why that is more important than the sum itself is because once you know that a series is convergent, you can just apply the definition of sum to find the sum or estimate the sum. You calculate the sequence of partial sums, then the more terms you see in that sequence, you will start to understand where that sequence is converging, and that's how you can guess at the sum. And then maybe if things are really nice, then you can prove that that sum is this perfect value. But in any event you can estimate the sum. So convergence or non-convergence is more important to know than the actual sum itself when the series is convergent. And lastly, there is one particular type of series whose convergence is very easy to, convergence or non-convergence is very easy to guess. And in fact, non-convergence is not present here, because this type of series, next type of series we are going to consider, by its very nature, these are all convergent. And they are called telescopic series. So that is the last result of this section. It's not that important, but it can be mentioned, of course. Lemma 15. Telescopic series. And the statement is this: let AN be a sequence of real numbers converging to 0. Then the series summation of, for some reason the author is choosing the index to go from 0. You can in fact make it go from any m actually. Converges to the first term itself. First term means first term of the sequence. When we will prove this, you will see that due to the nature of the terms, individual terms which are themselves differences, a specific type of differences, there are many cancellations, and that's how we have A naught, because after A naught whatever else appears they eventually cancel out, and in the long run you don't have anything else, anything other than A naught. So that's why the sum is A naught. And for this, the exercise 6, and this is where the section ends. So in the next video we are going to tackle the exercises and properly finish this section. In the next video itself we may not be able to finish everything, but in the part after that, of course, we will finish the things. Not many things are there. And once this section is over, then in the next section we will see that infinite series where all the terms are non-negative real numbers, they have a very nice theory of themselves, from which many things will follow. So that's just it for tonight. If you want to say something about these things or make any remark, positive, negative, whatever it is, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. And this coming Tuesday we are again going to see group theory from Herstein's topics in algebra. So with that I wrap up for tonight. So see you on Tuesday with Herstein's algebra. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.